in this lecture, I'm going to give you a short intro on recent climate change prediction. Then we will go through how the climate is changing in northern high latitude, and then the consequences of these changes. We are waiting for the 6th IPCC synthesis report, which was delayed due to COVID. Now is expected in 2022. In the meantime, there are several special reports that are of interest for different topics. And for the Arctic, there is the ocean and cryosphere in a changing climate report that just came out September 2019. And I will select some of the most up-to-date prediction from this report. So one of them is the prediction of how CO2 will increase under different projections. So we discuss what is happening here, okay? Now, what we will do is discussing what will happen in the future. So over here, as you can see, which is actually very important, it's what will happen will really depend on how we implement the climate legislation. So for people saying, oh, there is no way we're going to do anything about the climate, it's actually not true, because the CO2 concentration will have will be majorly influenced by how our policy decision. So what are these two? So these are the projection RCP 8.5, RCP 2.6. What are they? RCP is a representative concentration pathways. So they are basically scenarios that includes some sort of response of climate change to our policy. Okay, so depending what we do, we're gonna have either one or the other one. Okay, so if we implement a really aggressive legislation to reduce fossil fuel use and use also some capture, CO2 capture methodology, we will have a lower emission, of course, and a lower CO2 concentration. Okay. The other concept is CMIP5. So this is so basically this is how these curves are generated. So of course each model has a different parameterization, has a different way of estimating stuff. So what this CMIP5 does is put together a bunch of models. So it's a couple model intercomparison project. Basically put all the modelers together in the same room. If maybe they can find some sort of agreement on how the on what the prediction of the CO2 concentration will be. So it's in a way it's trying to average a bunch of model outputs to try to give a wide give a more robust estimate, because when you're trying to put, when you're relying, you're putting all your eggs in a basket, you're relying only on a model, of course you might be in trouble if that model has some issue. So if you put a bunch of models together, then it's safer. Now, we talked about these two scenarios. RCP 8.5 is basically business as usual, is what we are doing right now. So well, not exactly. We are trying to do something, but we are not doing enough. So let's say the RCP 8.5 is basically a high emission scenario in the absence of any policy. The RCP 2.5 instead is really when we really implement major climate legislation to prevent CO2 emissions, okay? And trying to, basically this is what the Paris Agreement is trying to achieve. So this high chance of keeping global warming below 2 degrees. Now, how this impact the change in temperature over the short and the long term. As you can see, that the from the exponential growth of the RCP 8.5, the big difference is not in the near term, but is in the at the end of the century. So the longer in time we go, the more there is going to be a runaway situation in which we're going to be in big trouble if we don't do something more aggressive. And how this is going to impact the temperature, the blue line over here, that's what we would like to achieve. So keep the temperature below 1.5 and definitely below 2 degrees. And this is when we are not doing anything. As you can see, that by the end of the century, it's going to increase up to 4 degrees. Now, this change, how this physical changes, so how this warming is affecting the cryosphere. There has been a shrinking of the cryosphere, of course. We are losing ice sheet and glaciers. These are the last estimates. So there is very high confidence that we are losing the lot of ice sheet and glaciers. There is also a reduction in the snow cover. There is a high confidence there too. And the sea ice extent and thickness and thickness. thickness. And then also we are losing permafrost. So permafrost temperature are increasing. Permafrost is the permanently frozen ground. So what is it? It's basically a chunk of soil with a lot of organic matter stored inside that is below zero for at least 2 seasons in a row. So this is basically for 2 years in a row. This is basically the definition, but it's basically something it's frozen, is locking the carbon. So if we are increasing the temperature, as soon as the temperature gets to above zero, then we lose this permafrost. Decomposition, actually, for the permafrost, the organic matter decomposition also actually happens also below zero, as you read from the papers that are included in the discussion, and from many other body of knowledge we currently have. What does it mean? So the interesting thing over here that actually the projections are lower than the observed change, which is already showing you that some of the modelers are struggling to be able to account and properly predict the rate of change. So the rate of change is much higher. The observed rate of change are higher than what we are predicting. And you see this also from this paper that came up a few years ago. It was looking at the snow cover extent. So the red line are from a NOAA product that is basically showing the snow cover extent, SCE, versus the ensemble mean on the models and plus or minus a standard deviation. As you can see from these red triangles, what we are actually observing is much more dramatic than what we are predicting, which it's really worrisome because already some of the predictions are showing a really strong impact on the environment. And if what we are observing is actually higher, it's very worrisome for being able to estimate the full extent of the impact of climate change from Arctic ecosystems. Now, why this is happening? Because there is something that's really peculiar of northern high latitude ecosystem, which is called polar amplification. So basically anything that happens in the northern high latitude is amplified by a variety of feedbacks that are related to snow cover, to a bunch of stuff. This breaks it down, but the most important thing is really the presence of snow and ice. So what does it mean? So if you have something that is white, is a white reflecting surface, then it reflects the energy entering the system. If you lose that, then you can have basically a darker surface. It absorbs more energy. So basically this creates a positive feedback on the climate. So basically, the Arctic, the positive and negative, the positive feedbacks on the climate in the Arctic are very extreme because of the presence of ice. So you lose this white reflectant surface for increasing temperature. Then you have, because you lost them, you have more increasing temperature, which further feeds on this general Arctic warming. Now, another of the feedbacks are the present large amount of carbon that is stored in the soil. So the northern ecosystems, you have permafrost, as I already mentioned. So you have a lot of carbon inside the permafrost. So if you start increasing the temperature of the permafrost, you can have, you can stimulate the decomposition of organic matter in the permafrost. You can release the carbon increase the CO2 concentration. The CO2 concentration traps more heat, and you have another feedback. So this is a wordle that is showing basically the association, the most frequent words in a text, which is also a way of showing some of the association between the words. So when you, in a text, you have permafrost, you have loss, release, warming, thaw. So you have a bunch of, you can see that the general knowledge is we are losing the permafrost, and this permafrost is releasing carbon. And this is basically linked to warming. Now, how does the permafrost look like? So this is a picture from Siberia. You can see you have a chunk of permafrost outside of the ground underneath boreal forest. So you have basically a chunk of frozen soil, you can see from this. Now there are different types of permafrost in the northernmost areas. You have continuous permafrost. What continuous means? You have basically a chunk of soil, a chunk of frozen soil that is continuously frozen. So you don't have anything that can, for example, drain the water. Why this is important? It's important for the hydrology of this system. You basically are really wet soil. There is standing water in most of this. Depends also on the depth of this of the permafrost, where the frozen soil starts, but basically it's the wetlands, the very existence of these northern wetlands are related to this, the presence of this continuously frozen ground, which prevents water drainage. There are a bunch of lakes and a bunch of ponds, and it's a very wet ecosystems. When you move south, you start to have these through talic, that's how they are called. You can basically where you can have some drainage. So like in this area of discontinuous permafrost, they are usually less wet ecosystems, because of course you can have drainage in between this frozen permafrost spots. The more you go south, and you have progressively from the discontinuous permafrost, you can have sporadic permafrost. Sporadic, you have a bunch of less frequent areas of frozen ground, and then isolated you have just small chunks of frozen soil in between a large area with no permafrost. Why do we care about permafrost? Well, permafrost, it's, as I already mentioned, store a lot of carbon, but the carbon is not the only reason. The permafrost, it's also the thawing of the permafrost is also affecting the stability of the infrastructure that are being built across the Arctic. As you can see from this map, there is actually quite a large amount of areas where there is a high risk of high risk of damage to infrastructure due to permafrost thaw. a natural phenomenon, but it's pretty interesting. It's the what's happening in the boreal forest because of the thawing of the permafrost. It's similar to what we saw for the building, but because it's natural, it's less worrisome. It's more interesting to mention is this drunken forest. The drunken forest because the tree look kind of drunk, but you see that it's something interesting in areas where there is permafrost. So you see this boreal forest with these trees that are all crooked. Now, permafrost and carbon. Why permafrost is important? I already discussed how the permafrost affects the carbon, but there are different steps. So is the carbon, the carbon stored in the permafrost is not necessarily released right away. So more with warming, you can have, you can release some of the carbon, but you also release some of the nutrients that can stimulate the plant growth. So initially, as you can see from this figure, initially you can have actually an increase in the storage of the carbon, as you can see, because you have more nutrients available for the plants. So maybe the net effect is more carbon in the initial phase of permafrost thaw. But when you have a further degradation, in this case, the plants still grow faster, but they release from the carbon decomposition in the permafrost outweigh this increase in uptake. So basically, on the long run, you lose carbon with more permafrost thaw. Now, and this is, as I already mentioned, a positive feedback on the climate. So how much carbon is in the permafrost? There are different estimates, and there is still quite some range in these estimates. There is some disagreement, not too bad, but there is some disagreement because it's really hard to actually estimate how much it's there. But the two numbers that are most frequent are these 1,300 petagrams of carbons, which is petagrams and gigatons is the same thing, but it's basically about double of the atmospheric carbon pool. So you can understand the relevance of this. So this is a paper from 2014. The number that is there for the permafrost is 1,700. So the reference for this 1,700 is actually some papers from 2008. So it's even if this was published in 2020, actually they are relying on some of the estimates that are older, and this guy is newer. And also the IPCC 2019, the special reports uses the 1,700. So there is a little bit of a disagreement, which is 400 gigatons of carbon, which is quite a bit, but not too bad. I mean, given the complexity of measuring this. And to this carbon, so the problem is when the carbon is stored in the permafrost, everything is fine, we are happy, it's stored there, it's not affecting the atmosphere. The problem is when the carbon starts coming out. This is one of the early paper, now it's 15 years ago. I remember when I was a student, I thought, oh, this is a surprise. I was a student when this paper came out. It was a surprising. We were in the field. We actually met the scientist who was collecting these samples. And so the bottom line is that some of this methane is actually, the methane is a really important greenhouse gas, as you know, and some of this methane is stored inside the permafrost, and now with warming is coming out. And you can see the concentration of this bubble coming out of the Arctic. These are Arctic lakes and ponds, is actually so high that you can light it on fire. Now, what is this methane? It's actually coming from methane hydrates. So methane hydrate is basically a crystal that of ice that is trapping highly concentrated methane. You can see there are large reservoirs on the coastal area across the globe. So why the Arctic is important? Because these deposits are shallower. So it's easier that with melting of the sea ice and warming, which is faster and more intense in the northern high latitude, some of this methane can come out. This is a study that actually looked at the methane concentration from some of these bubbles trapped in the sea ice. So this was a cruise that measured the CO2 concentration of the Siberian coast. And they found in some of these frozen bubbles a concentration of methane of 11,400 ppm. But this is like orders of magnitude higher than what's in the atmosphere. As you can imagine, if you start losing this methane and emitting it to the atmosphere, you're going to have a big impact on the climate. Of course, nobody knows how much is going to come out. We are at early stage of research on this. So that's what's exciting and interesting. We don't really know how much, and we don't really know how the climate is going to affect it. But the bottom line, if we are losing some of the sea ice, it's also where this methane is trapped, then we can have a further emission. But the bottom line is that we don't even know what's there. So this was one of the studies. This is a review that actually looked into the study. So the earlier studies were actually funded by this energy company that were trying to figure out if they can use these methane hydrates for energy. So initially they thought there were like 10,000 gigatons of carbon, and right now the more recent estimates are between 500 and 2,500, which is still a lot of carbon. And this goes together with the number of publications. So it's not that the reserves decreased over the last 30 or 40 years. It's just that we have more publications, so we have more knowledge, which tells you the science matter for the environment. On the impact of science on society is actually major if we use our science and we communicate our results in the proper way. So now, big question. So is the Arctic a carbon source, and is the carbon we store over thousands of years being emitted to the atmosphere with climate change? A way to answer this question is using isotopes. I'm not gonna go into details. I just mostly want you to understand the main concept. So you have a background production of, basically you have some energy coming from the sun that is exciting these neutrons. The neutrons are getting inside the nuclei of different elements and creating this isotope. So it is a natural process. But the important thing is that in the 50s and 60s, we were going around bombing stuff, crazy stuff. We were doing this nuclear testing. This nuclear testing increased the presence, because you are putting a lot of energy there. So this huge energy is increasing the amount of these isotopes. So it's enriching the isotope. When you hear about enrichment or depletion, that's what it means. So if on the long run, in simple terms, if before this nuclear testing, you had a level, this concentration, this percent per mil of this specific isotope that is very low at this number, and then you in the 50s and 60s, actually up to the 70s, almost the 70s, you had this huge increase. Then you can use these numbers to try to give some sort of a footprint of the age of the carbon that is being released. So the recent detritus is enriched in carbon-14 because it's coming from here, okay? The old carbon instead is depleted because it's coming before this nuclear testing happened, okay? So this has been shown as a way, this is one of the foundation papers that actually showed it, demonstrated we are actually losing carbon from the Arctic because of warming and climate change. So the carbon loss increases with the extent of the permafrost thaw. So the more extensive is the permafrost thaw, the more old carbon in both in grams of carbon and proportion of carbon is increasing. So we are losing carbon that has been stored over thousands of years right now because of this increased permafrost degradation. And this is also the carbon, so this old carbon is also the carbon that is bubbling up from these methane seeps. So there are like, this is following up to some of the previous paper in which I show you the methane with the fire coming out. This is actually quantified and trying to attribute also the age. They found 150,000 seeps of this permafrost coming out from Alaska and Greenland, and they also found the ages, which was ancient radiocarbons, okay? Now, this is even more worrisome because this permafrost thaw is will continue to happen, and it's basically there is a very high confidence that an extensive and widespread permafrost thaw will happen by the end of the century, and there is a decrease between 24 plus or minus 16%. For the aggressive mitigation scenario, and up to almost 70% for the business as usual scenario. So it really tells you that billions of tons of permafrost carbon can come out as a CO2 and also methane by the end of the century. Now, the Arctic is greening. There are people that are also saying, oh yeah, but then what about vegetation? So we have all this end of the world prediction for the permafrost carbon, but the vegetation is increasing. Yes, it's true. There is an increase in biomass, which is shown by this green in most of the Arctic, not all of the Arctic. And this is a recent paper that I was actually reading a few days ago, which quantified the greening and also what's driving it. So this shows that a positive correlation with warming. So of course, these are temperature limited ecosystems. If temperature is increasing, the productivity is increasing. Not everywhere. You can see this red area when you have a negative NDVI. These are areas which they are mostly related to drying, when you have which is limited vegetation productivity, but most of the sites are increasing. This is the paper if you're interested. So bottom line is the greening is occurring in most of the sites, is related to air temperature, soil temperature. The browning is happening in some of the sites which are cooling and also are drying. Okay, so you have the water, most of the sites where you have temperature is limiting, but no moisture, they are doing well, but sometimes moisture and sometimes also you have cooling, because even if the warming, it's the overall trend that you have regional differences. And most of the sites are, however, showing an increase in plant productivity. there is an increase in the biomass of the shrub, there is a variety of different processes there are some negative and positive feedbacks, but the most striking impact of the shrubs is that they are darker, they stick out of the snow, so they increase they trap more energy because it's a darker surface. They decrease the albedo, so there is a more energy being trapped by the presence of increased abundance in shrubs. We talked about the early snow melt, so we show that there is we are losing snow. The snow cover extent is decreasing, but something that it's also decreasing it's the snowfall. So basically, the snowfall is happening later in the year. So this is increasing the growing season length. Now the question is, what a longer growing season length how it will impact these ecosystems. Well, there is a lot of discussion about this. Is a study that we put together by collaborating with several other researchers in Alaska. Some of the concepts here. So NE is the net ecosystem exchange, which is the balance between GPP, which is the gross primary productivity. So it's basically the photosynthetic uptake of the plants or the vegetation. Everything green that it's there is uptaking carbon. Now, some of this carbon is being lost by the ecosystem respiration, which is the respiration of the plants and of the soil. So everything it's being lost. And NE is the net of these two processes. So what we found was that even if GPP, so plant productivity, is stimulated by temperature, the growing degree days is basically a metric of temperature, and also respiration is stimulated by increased temperature. The net of these two processes, so the response of the net ecosystem exchange to growing degree days, is unclear. So we didn't find any relationships. Now there are a lot of remote sensing studies that are showing greening, as I already showed some of them, increasing the NDVI, but increasing the NDVI tells you the increase in GPP. So is this part, so it tells you how much like green the vegetation is. It's a proxy of biomass, the greenness that is there, but does not tell you necessarily what's the net impact on the carbon. So when you actually measure the net impact, you see that these increases are not necessarily translating in more carbon being stored by the vegetation. For people that don't work on in the carbon flux stuff, this sometimes is a little bit puzzling, because they say, no, but I know the vegetation is increasing, vegetation is greening. Yes, it's greening, but the carbon stored is actually the balance of the vegetation productivity and the ecosystem respiration. So if the temperature is increasing, also ecosystem respiration, so then you might actually have a loss in the carbon with increasing temperature. And in this case, with increase in growing season length or growing degree days. Sea ice, this is something that it's strikingly changing. So the sea ice loss is incredible. So I already discussed this concept. The sea ice, it's one of the most important positive feedback actually happening in the Arctic. Now, not only we are using the sea ice, but we are also using the total coverage, as you can see from this, but we are also losing the multi-year ice coverage, the ice thickness. So why do we care about this? I will go into more details later on, but basically, for one thing, they are affecting some of the ability of the native population. I will get as a few slides talking about this. If you have thicker ice and more resistant ice, because it's a multi-year ice cover, then it's stronger, and you can travel on top of it to hunt. And also the wild fauna is affected by the ability of using the ice, the resistance of the ice to travel and hunt. To the cover, so a decrease in sea ice coverage, as you can see that has a huge potential economic impact. If you have perennial ice cover, then you cannot travel this is the Northwest Passage, the notorious Northwest Passage that our society tried to use for hundreds of years to be able to transport goods, because as you can see is a much shorter route and saves a lot of time and money. So it has a major economic implication to be able, you see how much shorter is, for example, also from Europe to travel to Japan. I've been to this meeting in Japan, and there were so many presentations. A few years ago was an Arctic meeting, and there were so many presentations of people trying to figure out when the sea ice will be gone from these areas, so they can basically send all their goods through these northern sea routes. But basically the economic impact is huge. But also on the other hand, there are implications for the risk for the Arctic marine ecosystem and the coastal communities. So you can imagine if you have more shipping being routed around these areas, you have more invasive species, more pollution. These are usually areas that have not seen much of a human influence, but this is changing rapidly. Now, the sea ice reduction can have also a huge economic impact for the increase in coastal erosion. So this area gives you, this map gives you an idea of the most the areas more susceptible to erosions. So you can see there are several areas with also people living there. So the actually low-lying coastal zones in total globally are about, there are 680 million people living there. And this is nearly 10% of the population. And going back to the multi-year ice, together with the sea ice cover and the ice thickness, the also the polar bear, this is a charismatic megafaunas, and might get people, might convince people to do something about climate change. The polar bear actually relying on the sea ice for hunting. They will not survive if the sea ice is gone, because they need to sit there waiting for the seal to come out of the ocean to hunt, and they cannot travel, they cannot swim forever because they need to rest on the ice. So basically the sea ice is going to affect them. This is a picture of this horribly thin polar bear that actually, when I read this article, it turned out that the guy was hurt in a fight, so it had nothing to do with the sea ice. But I think the photographer really liked this picture, and I'm using it in a lot of the talks that I give, and everybody, all the audience, oh, it's like when they see this poor polar bear. So it's using is a little bit dishonest, but serves the purpose of trying to get the attention of people. So the bottom line is basically we need to do something about the sea ice because it's affecting polar bears, but not only polar bears. So polar bears are more charismatic because they look, I mean, of course, they have this beautiful animal, but actually even the marine food web in the Arctic is very complex. So once you start affecting the sea ice, you're affecting a lot of the different parts of this marine food web, including the ice algae, which are already being affected majorly by the sea ice loss. Briefly on the impact of climate change on Arctic population, the IPCC report on the cryosphere had a section also dedicated to this. The food and water security were being negatively impacted by change in the snow cover, lake, river, and permafrost, blah, blah, blah. And these changing are affecting majorly the indigenous community. By working in the Arctic for more than a decade right now, talking to the indigenous community, they are close to our field site, they are really being affected by how, by their access to the hunting. So for them, hunting, it's a really important part of their livelihood. The price of food in the Arctic is incredible. So a lot of this community, they have lower income and they are relying on hunting. Also, hunting is a social and a cultural thing, which is really important, the hunting of the whales. So their life is being majorly affected by the loss in the sea ice. They are using the sea ice for transportation and hunting. Of course, if the sea ice is less thick and less resistant, there is a problem with them being able to travel. And also they are the traditional indicator that they are using are not currently working because of this increase in predictability of the weather. Last topic, few minutes left, the cost of climate change. When I hear people say, oh, we are not doing anything on the climate because it's too expensive, we cannot hurt our economy, we need to think about our economic growth. Actually, climate change, not doing anything about climate change is costing more than doing something about it. This gives some of the estimates, and this is a paper we will discuss. But the bottom line is that these estimates are an important part of the global GDP. Of course, as you can see, and as you read, there is a huge uncertainties. There are uncertainties because we don't know how much the climate is going to change. We don't know how much the change in the climate will result in a release of the carbon from the permafrost. But the bottom line is that this is important. We need to do something about it. Summarizing everything, importance of polar amplifications, positive feedback. So understand that these concepts are important. Large amount of carbon, why the Arctic is important for the climate, because there is a large amount of carbon and large potential for this carbon to be released. And also how the important concept of sea ice and decrease in snow cover are important positive feedback, how we are changing and affecting the marine food web and the native population. And just to finish up, not doing anything can be very expensive. So if somebody tells you we need to grow the economy, we say, well, we grow the economy by actually decarbonizing our economic model, finding alternative way of using energy, decreasing our footprint. And actually the most important thing is that the costs of climate change are being paid by the most vulnerable societies. So they are some of the society that are less prepared to be able to deal with these issues.